Okay, now let's move on to module number 2 with deep autoencoders. The module also has similar objectives. I want you to know the effects of deep versus shallow autoencoders, implement your own deep autoencoder, and apply a deep autoencoder to the dimensional reduction problem and visualization as well. If you just joined us, I just want to point out that we have some resources available at this website, and I'm asking you to go ahead and check it out because we're modifying the code and giving suggestions how to modify the code and run it by yourself. It's very important that you run the code in the collabs by yourself. Okay, welcome if you're just joining us. But as I was saying, on deep autoencoders have this name of deep only because we're referring to a larger number of layers with neurons in them. All of this, there's a concept called deep belief networks, which deserve its own tutorial, and we can talk about it for hours. But I'm going to put simplifying at the risk of oversimplifying some things. I'm going to point you to this paper by Professor Hinton and Stutzkever in 2008, in which they're discussing things such as deep belief networks and deep learning. What we know today as deep learning and deep belief networks by talking about restricted Boltzmann machines. These type of machines operate in a restricted sense that some of these neurons or entities can only see data at a time. So in this case, in the picture here, there are some that are visible, some are hidden units. And the visible units can produce output, can also receive input. Hidden units can communicate with the visible units back and forth. And there's this nature of adaptation and the way these are communicated, and they're learning back and forth to share information. And so this idea, when you unpack it and unfold it and try to visualize it, is as if there were many pairs of layers that communicate with each other. And later on, this idea of deep belief came to produce breakthroughs in understanding what really happens in deeper networks or deeper layers of networks. There's this paper I went into 2016 that also showed that deep networks lend better representations if you have these pairs of layers that are trained first in a similar way that restricted Boltzmann machines. And then once these are trained, then you train the next pair. And once this pair is trained, you train the next one until the whole thing is trained at once. But there's not a process in which all of them were trained simultaneously. This only shows that these deeper networks learn better representations in a similar way that restricted Boltzmann machines do. And so in deep autoencoders, we're going to add more layers into the model, hoping to have a similar effect that deep belief networks do have, in which by having deeper structures, that the things that they're learned there are more interesting. To do that, we're going to recur to one interesting tool called batch normalization. I'm just throwing this concept right here. It's a tool to prevent gradient exploding gradients or vanishing gradients if it's a problem, a documented problem. And also it may lead to faster training by regularizing the model. Regularization is important, as you may know, in machine learning, because it leads to more stable problems or more feasible solutions. And so this is a nice tool to have in your toolbox. Batch normalization will be used in the middle of a neuron as soon as it communicates from the previous neuron after its own activation function. It normalizes that multiplicative and additive portion of the neuron before it is outputs to the next neuron with its own activation. And so that is sort of what this does. It normalizes an output so that whatever happens at this point in this neuron is not a problem that can cause a domino effect when a specific neuron is firing more than the others, for example, or has a very different range. Simply, you can import this in TensorFlow Keras as batch normalization is a layer, and we simply attach it between a dense layer and its activation. That's it. All right. Just to show that these things work, here are performances or model reconstruction losses with batch normalization and without batch normalization, with the training set and the validation set. And so the loss that is always under or lower is that belongs to when we use batch normalization. A second tool in your tool set when you're doing deep learning is also a dropout strategy. Dropout, it's genius. Originally also proposed by Hinton and Srivastava. In 2014, we know that this has the ability to reduce overfitting or the chances of overfitting, and can lead to more robust networks that generalize better. The idea of dropout is simply that if there is a neural network, one of these neurons is going to be, if dropout is applied on it, there will be no incoming connections to that neuron, and there will be no outgoing connections from that neuron to other neurons. This is completely done at random in every epoch. So the fact that in this epoch or training step, this neuron was disconnected from the network doesn't mean that in the next iteration it will be remaining disconnected. In fact, chances are it won't be disconnected due to the random nature of these things. So what this causes is to reduce the number of bully networks or neurons. It's a way of explaining that if there is one neuron that learns the whole pattern really, really, really well, it tends to dominate the network, while the other two neurons tend to be ignored by the following neurons in the layer. By disconnecting neurons at random in every training step, every neuron has to pull its own weight and learn the pattern by themselves. So this, as I said, reduces overfitting and produces good generalization. We import this simply as a node layer, and we usually apply this prior to a dense layer or prior to a layer that has that is learning something. As simple as that. Okay, so just to prove a point, the reconstruction loss on an experiment that uses dropout always usually produces very low losses or smaller losses than if you don't use dropout strategies. Okay, now let's implement or introduce this data set. The CIFAR data set is a data set that has it's supposed to learn feature representations of these several objects. First, airplane, automobile, bird, cat, deer, dog, frog, horse, ships, and trucks. Introduced in 2009. These images are rather small, Compared to the numerals in NIST, which are 28 by 28, these are 32 by 32, a little bigger, but it's not enough resolution for us to see details of a dog, for example, but you can still see that there are legs, there's a tail, maybe ears, collar, and that sort of thing. In trucks or cars, you can still see wheels, maybe windows, and maybe some other features like doors. So this is an extremely difficult problem to solve. So we're gonna use a deep autoencoder for this one. And we're gonna put here about 20 plus neurons, layers. So we start over here. We're gonna have an input image. We're gonna put a dense layer with 1048 images, followed by a ReLU, rectified linear unit, 1024 neurons, followed by batch normalization, followed by a ReLU, followed by dropout. We're gonna repeat this pattern of layer after layer with different number of layers. So it is again dense, ReLU, dense, batch norm, ReLU, dropout. Same over here, but at the end, we're gonna have a tanh function, which is a hyperbolic tangent. And it is different from the sigmoid function or activation function in the sense that a sigmoid would provide ranges of values between 0 and 1, and then hyperbolic tangent goes from -1 to 1. That's it. Both are differentiable in gradient descent, so those are nice. And the reconstruction process goes back like this. So we're inverting number of neurons as we go back. As you can see in the example in this picture, this sort of model will reconstruct this image like that, or this car like that. The colors seem to be correct, but the details of the picture seem to be missing. So when we train this, the binary cross entropy is minimized as we go, and the model keeps learning, but there's a point in which it doesn't improve and we have to stop it after 200. This model would look like this. This is part where we show how to load the data set. And it's part of Keras as well. And CFAR 10 is right there. And we do the same as in NIST. We declare the input dimension because now it's color. It's going to be 32 by 32 by 3 because it has 3 channels for color. The latent dimension is going to be 64, not 2. So we cannot display or plot the two like we did in NIST in this two-dimensional space, the latent representations, unless we use a third-party function. But we're going to do the same. We move the range from 0 to 1, and then we also do convert this from a three-dimensional matrix of 32 by 32 by 3 into a vector. So all of these functions, or all these layers that I described earlier, are simply defined like this: dense followed by number of units, and the input vector, we declare it. Then we specify an activation function. Prior to this, we could define the activation function right here in the same spot as the dense layer. But I just wanted to show also that you can do it outside and specify the activation function outside. This will also allow us to put a batch normalization layer in the middle of the activation function and the output of dense layer. Finally, we attach a dropout. Point 2 indicates the rate of neurons that are going to be disconnected in every training step. So in this case, it's 20% of the neurons coming out of this layer are going to be disconnected. We repeat the exact same pattern, but with different number of layers. Neural units are different, the rest is the same. And we do also repeat, finally, up to having the encoder, which is using a hypervalid tangent activation. This, though, is going to be a 64 because it's latent dimension. Then we can declare our latent encoder model that'll take input and then the encoder layer as output. Then we're going to start building our decoder. So once we have the latent representation here in encoder, we're going to build it back or reconstruct it. And it's similar order but backward. So we start with a dense, followed by batch norm, activation ReLU, dropout, then dense activation, dense batch normalization activation. And then we keep doing this until we reach the dense layer of 2048. And finally, another dense layer with the same number of input dimensions as the data. And we have an activation that is a sigmoid instead of a ReLU. We need the sigmoid because the data initially, remember, was normalized to be 0 and 1. So the sigmoid is necessary. We're going to also declare a model, an autoencoder. This is the one that is going to be optimized or trained. And we're going to use the model, the latent encoder, to simply take input data and put it in this latent representation. We're going to use a different optimizer this time. Last time, I think we used SGD in the first experiment. And the second one, we used Atom. This time, we're going to use RMS probe. But again, you can actually use Atom if you want. I just want to show you something different. And also show you that you can also specify learning rates and other parameters as decay. So in order to know how to mess with these optimizers, you have to dive a little bit and read about what the algorithm is all about so that you can do a good job in choosing these parameters. Just so you know, a smaller learning rate tends to train slower, and a higher learning rate tends to train faster, but can lead to instabilities in the models. Just a warning. Okay, so the training is the same as before. We fit using training data, and we target to reconstruct exactly that training data. We're gonna do this for 200 epochs. 10,000 elements is batch size. I recommend you do smaller batch sizes than this. So what I want you to do is choose a smaller batch size than 10,000. Try 100, 200, 500, or even 20, 50. See what happens. Just experiment with this, and you can see if there's a benefit in using smaller batches or larger batches. In the next step, we can visualize that after training, fitting the model, something interesting happens usually when you have these dropout layers, that there is this increase in the test set, in the error, but then starts converging back. Don't panic. This is usually normal when you use dropout. But the gain is that in the test set, the model is doing better on the test data than on the training data. It's learned to generalize better. Just to give you an example of what the reconstructions look like when we actually call predict on autoencoder with test data. This image was reconstructed as that. These two ships were reconstructed as this. Let's look at the plane. Look at the frogs over here and the car. What do you think? I'm thinking that in some of these, the colors seem to match. The details are completely gone. Almost, you cannot tell what is it. I can sort of tell this might be a plane, but I'm really pushing it. But in some occasions, the color is also a little bit off. So we're gonna say that the performance on this data set for a deep autoencoder didn't work well as we expected. And to show this and to prove it, we can take that 64-dimensional latent representation of every item in the test set and use a tool called UMAP. I'm not going to explain what UMAP is, but it's another way of visualizing data that is higher dimensional in 2 or 3 dimensions. So this looks like a bear, which is the mascot of my university's Seeking Bears. But you don't see very discernible groupings or clusters of data. And there is no clear separation of pink dots and yellow dots right here, as you would see with NIST, for example. So what I'm showing you with this is that although deep autoencoders are really, actually really good, there are some problems that they cannot solve efficiently. And this is one of them. So I'm gonna just say out loud that for computer vision, for general computer vision problems or object recognition, maybe autoencoders based on convolutional layers rather than dense layers will work a lot better and will work actually a little bit faster as well. But to show that deep autoencoders are not actually bad, I'm gonna show you a demonstration of what happens on with NIST data, a relatively simple data, because if I didn't say it earlier, CFR10 data sets are really complicated. They are really complicated to resolve. So you're gonna find it very challenging. But NIST is it's a sort of medium complexity data set. It's perfect for showing that things work or don't. And I'm going to do this configuration of a deep autoencoder, same number of layers, it's just a different number of neurons. That's it. We're going to have 512, 512, 256, 256, 128, and then 2. And we're going to repeat, working our way backward to 784 dimensions. Spoiler alert, the model seems to perform really well. There's the spike that I told you about with Dropout again. And these are the reconstructions that you expect with NIST and a deep autoencoder. If you remember, first when we used a shallow autoencoder or traditional autoencoder, wasn't that deep. The details of number 4 here were gone. This looked like the 9, and this one also looked like the 9. As you can see, although some details are lost, you can still tell that this is a 4, 4, 9, a 1 or 0. Although this little tail on number 4 in the reconstruction is gone. Some or shape of the 9, it's also gone. Some tail here on the 0 is also gone. So it seems like this autoencoder is doing well in capturing the data, and we can show this by looking at this two-dimensional representation, which, by the way, we're doing it here going back to 2 instead of 64 like we did with CFAR. So we can actually display this. You can clearly see that there are some groups in this picture, and there are nice suppressions. And again, this data knows nothing about labels. I'm just using the labels to display the data here, but the model doesn't know about a label. So I would like just to think about what you did. If you messed with the problem before and you changed or altered the number of neurons or the optimizer, or you messed with something, what was the effect of doing that? And thinking further, what is the good thing about dimensional reduction? Why is necessary today? And more importantly, what are we losing when we do dimensional reduction in your thoughts? When you reflect on this, what do you think we lose when we use fewer dimensions? If I use 2 dimensions only in this latent representation, what am I losing? And a follow-up question would be, how can we take advantage of the process to do something else? How can we take advantage of the process to do something else? So let's have a short discussion on this, and I'll try to answer some of the questions, and you may interact with each other there if you want.